the introduction, and I'm very excited to be here. Great to see so many colleagues. Yeah, so as Martin mentioned, my name is Michael Metzger, and today I would like to share with you two discoveries that we made in our partnership with Tesla. And they deal with lithium and sodium-ion batteries. And in particular, I would like to talk to you about the role of the Jellyroll tape that's really found in any commercial battery cell, and how it can be a culprit when you want to develop long lifetime batteries with low rates of self-discharge. So, for us, self-discharge is really something that was driving us crazy in our laboratory. So we do a lot of tests on battery cells that operate at high temperatures. We do a lot of storage tests of battery cells at elevated temperatures. And of course, every lithium-ion battery in the world shows self-discharge. But under some conditions, the self-discharge rates can be really fast. And obviously, this is a huge problem for, really any applications where batteries are used. But of course, also for automotive batteries, right? That's something we want to avoid. And so here I show you an LFP graphite cell. It has a very standard electrolyte, 1.5 molar LiPF6 as the salt, and ethylene carbonate, dimethyl carbonate as the electrolyte. And we store this battery cell. It's a multi-layer pouch cell that we typically use in our laboratory. We store it at elevated temperature, 60 degrees C in this case. And you can see how the voltage of the battery cell goes down over time, right? So this is just 500 hours. It's 3 weeks roughly of storage at elevated temperature and open circuit. And you see the voltage of the battery cell goes down, right? It almost goes down to 3 volts. So this battery cell completely self-discharges in just 3 weeks. So this is, of course, a real problem, right? And we want to understand what is causing this rapid rate of self-discharge, and how can we get rid of it? How can we eliminate it? So the first thing I want to show you is what the electrolyte in such a battery cell looks like after the cell has been stored at elevated temperature. So we have a method in our laboratory how we can extract electrolyte from pouch cells, and then of course do all kinds of chemical analysis on them. But this is just a visual image to show you what happens to the liquid electrolyte in a battery cell. So this is the same electrolyte as I have shown you in the course of the presentation. I will just call it our control electrolyte. So this is the LFP graphite multi-layer pouch cell, and we extracted the electrolyte after the cell has been stored at 25 degrees C, 40, 55, 70 degrees C, right? And you can see how the electrolyte changes color. It goes to almost a dark red color, and clearly, some reaction products must have formed in this battery cell. So if we add 2% vinylene carbonate, which is a very well-known additive that passivates the negative electrode really well, you see that there is no color change at none of those temperatures that we store our battery cells at. So our first hypothesis as to why these LFP batteries show this rapid self-discharge and the discoloration of the electrolyte was maybe there's iron dissolving from the positive electrode. So we did the same test with NMC 811 cells that have the exact same negative electrode. It's the same type of artificial graphite. And you see the same color change, right? And again, if we use 2% vinylene carbonate, there is no color change in these battery cells. So what is causing this drastic change to the electrolyte, and is it related to the self-discharge that we measure in these battery cells? So we did a chemical analysis by gas chromatography on these electrolytes. Basically, this is a nice technique that allows you to identify the molecules that are created in the battery cell. So in order to make our life a little easier here, we just use a simple electrolyte formulation that only has DMC, dimethyl carbonate, as the solvent. We have no ethylene carbonate here. That sort of simplifies the gas chromatography analysis, but you see the color change is very similar for this electrolyte. And now we can basically take these exact electrolytes that you have seen in the picture and we put them in the gas chromatography machine. So the top panel, panel A, shows you the pristine electrolyte. And you know there are of course no species formed because that electrolyte was never in the cell. And we just see the DMC peak here at the low retention times, right? So and then in panel B and C, you see the electrolyte we extracted from LFP graphite cells and NMC 811 graphite cells when they were stored at 40 degrees Celsius, which is sort of a moderate temperature. And you see there are no major reaction products formed here in these cells. But what if we store the cell at higher temperatures? So here's the data for a cell that was stored at 70 degrees Celsius, you know, where we see this very drastic dark red discoloration and where we also see, you know, high rates of self-discharge. And you see there are a lot of new reaction products formed. And some of them are easily explained. So for example, the first major peak here, which I labeled TMP, that stands for trimethyl phosphate. And in fact, Martin's group published a very nice paper where it's shown that this is a reaction product between DMC, our solvent, and the LiPF6 conducting salt. Then to our surprise, we also found ethylene carbonate here. But remember, we did not add that to the electrolyte, right? So ethylene carbonate has been formed. And then the other molecule that we were really intrigued by is the molecule at about 18 minutes retention time, which I labeled DMT. That stands for dimethyl terephthalate. So that is a very unusual molecule, right? It has a benzene ring. How could that possibly be formed in our battery cells if we only have our linear carbonate as the electrolyte solvent? So we were very intrigued by this molecule. In fact, you can buy that molecule commercially, and we did a control injection just to prove that this is truly the molecule that we generate in our battery cells. Sure enough, it shows up at the same retention time, so we're very convinced that this is indeed formed in our cells. And you know, when you look through the literature, you find that a lot of so-called redox shuttle molecules have this benzene ring structure, right? And a redox shuttle, of course, it's a mobile species in the electrolyte which can shuttle charge between the positive and the negative electrode. So that could explain the self-discharge we were seeing. So that's sort of our candidate for what's causing the self-discharge in our batteries. But we did a simple test to show that DMT is truly a redox shuttle. So, you know, we have our pristine electrolyte to which we add the DMT molecule. If we do that, the electrolyte is clear, and we can pipette it on top of a lithiated graphite electrode. Here you see this nice golden piece of graphite, right? So it's a negative electrode which is at a low voltage, right? And if we put that electrolyte on this piece of electrode, after a few seconds it turns red, which is really in good agreement with the color change we have been seeing in our battery electrolyte. So now then we can take that red electrolyte back into our syringe and put it on a delithiated LFP electrode. So an LFP electrode which is at a high voltage, 3.65 volts. And when you do that, the electrolyte turns transparent again. So it's truly a reversible color change we're seeing here. So this is sort of the electrolyte after it has been in touch with the negative and the positive electrode. So the DMT molecule, it undergoes a reversible redox reaction. When it's reduced at the negative electrode, it turns red. And when it's in contact with the positive electrode, it becomes transparent again. So that's characteristic of a redox shuttle molecule. But of course, the question is, where does this strange molecule in our battery cells come from? So I want to propose a mechanism for how this molecule can be created in our cells. And you know, I want to start by showing you the hydrolysis reaction of DMC. So DMC is of course a very common linear carbonate used in almost all batteries. It would be same for EMC or DEC, right? So if you have some residual water in your battery cell, which is very hard to get rid of, you know, we dry all of our cells at 150 degrees Celsius, but even if you do that, there's always some residual water in the cell. So especially at elevated temperatures, you know, the DMC molecule can be hydrolyzed, and you get methanol that's formed in your battery cell, right? And then another reaction that can happen is you can electrochemically reduce DMC. And if that happens, you generate CO gas and a species which is called lithium methoxide. And this happens if you do not have effective additives that passivate your negative electrode. Okay, so if you have vinylene carbonate, for example, where you passivate your negative electrode first, then you would not have such a reaction. But in our control electrolyte, where we don't have that additive, we would form lithium methoxide. So if you have those two species, methanol and lithium methoxide, then you can, in fact, depolymerize PET. So there's a very interesting paper from Japan where they upcycle PET plastic waste by adding methanol and lithium methoxide as a catalyst. And then you can break down that polymer into its monomer, which is our DMT molecule that we found in the battery cells, and ethylene glycol. So we were very intrigued by this reaction because we have all those ingredients, but we didn't find ethylene glycol. And that's because ethylene glycol can react with DMC to form more methanol, and it would also form ethylene carbonate, which is the molecule that we were also detecting in our gas chromatography experiments. And then you could form a sum reaction where you basically have PET with DMC and catalytic quantities of lithium methoxide and methanol to give you the DMT redox shuttle we were finding and also the ethylene carbonate we were finding. So, we thought that this reaction really would make sense to explain the species we detect in our battery cells. But of course you have to convince yourself that it's really true, right? So what we do is we form a little pouch pocket, we call it. We take our pouch foil material, form a bag with it, and just add a PET film and DMC as the solvent. And then we heat it to 70 degrees Celsius for 5 hours and do gas chromatography on the liquid solution inside. And if we do that, we don't find any reaction products. If we add methanol, also no reaction products. So we replace methanol with lithium methoxide, still no reaction happens. But if you add all three ingredients, like in this reaction cascade that I have shown you, then indeed you form ethylene carbonate and the DMT shuttle molecule. And you don't even need the elevated temperature if you have those ingredients, even at room temperature. This reaction proceeds. So, we were pretty sure that this is what happens in our battery cells, but we were not aware that there's any PET in the cell, right? So what we did is we take these little cells, we get them from Lifan in China. It's a multi-layer pouch cell, you can see it up there, and we dissected it, and we, looked at any component of the battery and tried to figure out if there's some PET in there. So our first suspect was the separator, and we use infrared spectroscopy here with a reference spectrum for PET at the bottom. And you can see the separator is not made of PET. It's just polypropylene. So we looked at the pouch foil material. So the inside of the pouch foil, which is in contact with the electrolyte, it does not show any characteristic absorption bands of PET, but the outside does. But the outside is not in contact with electrolyte, so we also discarded that. But then we looked at the electrodes, and this is the unrolled electrode from this pouch cell, and you can see there are all kinds of tapes on the electrode, right? So there is a closure tape up top, and then there are also tapes where the current collector tabs are. And in fact, if you look at the infrared spectrum, these tapes, they show all the characteristic absorption bands of PET. So these tapes are made of PET. And you have to realize every lithium-ion cell that's made in the world, if you make it by winding or by stacking the electrodes, it would have tape to secure the jelly roll in place in the manufacturing process. So a quick summary of what's happening in our cells is, we have PET tape in our batteries. It dissolves to create this DMT redox shuttle molecule. The molecule, can diffuse to the negative electrode. It gets reduced, changes its color to a red color. And, for every molecule that's reduced at the negative electrode, for charge neutrality, a lithium ion has to leave the negative electrode, right? So then the shuttle molecule diffuses to the positive side and it gets oxidized. So you take away an electron, and for every molecule that's oxidized, a lithium ion needs to intercalate into the positive electrode. So if that happens over and over again, this redox shuttle reaction, then what you're doing is you're shuttling lithium from the negative to the positive electrode. So that's a self-discharge reaction, right? That's what happens on discharge. So, but then we thought, okay, maybe it's only our cells at Dalhousie University which have this PET tape. So what we did is we selected a lot of different commercial cells in various form factors, and we opened them up and we looked at the tape that is used in their Jellyrolls. So here are the infrared spectroscopy graphs for these different cells from pouch cells. So, you see all kinds of manufacturers here, LG, Samsung, Apple, and in all those cells, the Jellyroll tape is made from PET. Then we looked at some cylindrical cells, also some of them for automotive application. And, out of 14 random cells we selected, 12 of them contain PET tape. So how do we fix that problem with the PET tape? So in our cells, we found a very simple solution. So we just replaced all those tapes that are made from PET with polypropylene tape, PP. So that's a stable polymer, right? It's used as the separator oftentimes. So, and you can easily do that. You just make your tapes from polypropylene, and then we had our cells made with those tapes. And then we can do the same tests as I've shown you previously. So this is a high temperature storage test. If we have the PET tape, the electrolyte changes color, we get the DMT redox shuttle molecule in gas chromatography. But what if we change the tape? So here is a cell which has the polypropylene tape. Even though we stored the cell at 70 degrees Celsius for a long time, the electrolyte stays perfectly clear, and there is no DMT shuttle molecule that we detect in GCMS. So, our initial goal was we wanted to fix the self-discharge problem, right? So how does the self-discharge look? So this is the case where we have cells with PET tape, and we store them at 60 degrees Celsius with controlled electrolyte. Voltage goes down very rapidly, right? The cell self-discharges. If we have 2% vinylene carbonate, then you don't form lithium methoxide, your tape is stable, and the cell does not self-discharge. But we don't even need the additive, right? If we change the tape to polypropylene, you see the voltage of the battery cell, it stays high over these full 3 weeks, even with the control electrolyte. So there's absolutely no self-discharge anymore in these cells if you replace the tape and change it to polypropylene. So, and then lastly, just want to show you the effect of this for sodium-ion batteries, because we're very interested in sustainable batteries together with Tesla, right? And we're looking into sodium-ion batteries a lot. And here you can see cells that use PET tape. So this is just the capacity retention. We can focus on the middle panel, which is the normalized capacity retention. So if we use sodium PF6 as a salt in our sodium-ion batteries with just control electrolyte, then we thought, okay, this is a bad choice. The capacity fades very rapidly. So we changed to sodium FSI, which is another conducting salt, and we get quite stable capacity retention over these first 150 cycles or so. But you have to be really careful, because you can easily be fooled by data like that, because if you use PP tape, then in both cases, the capacity retention is very good, right? So the tape also has a big influence on the way sodium-ion batteries are operating. In fact, this picture, it shows you what the tape looks like just after 800 hours of cycling at room temperature with sodium PF6. You see the PET tape, polyethylene terephthalate tape, is completely decomposed, whereas the polypropylene tape is stable. So if we, use the correct tape and also some electrolyte additives, how good can our sodium-ion cells really be? That's sort of what we wanted to find out on this last slide I would like to show you. And we, of course, we have to compare those sodium-ion cells to a relevant benchmark. So this is a LFP graphite battery cell, and we did a lot of work on LFP in the past. The cell cycling for about 10 months at 40 degrees Celsius reaches about 90% capacity retention after 1,200 cycles at 40 degrees C. And our sodium-ion cells, when they're charging to 3.8 volts with advanced electrolytes, they can have better cycle life than LFP. So these cells are cycling for 10 months and 13 months respectively, and they retain 95% or 92% of their capacity. What happens at higher temperatures, 55 degrees C? There, the sodium-ion cells are even better. So they retain their capacity better than LFP graphite cells at elevated temperature. And now, for automotive applications, our target is to charge to higher voltages with our sodium-ion cells, to use advanced negative electrodes, and then hopefully improve the energy density that way so that they can become a real competitor for LFP. Okay, so in summary, I wanted to show you that, PET is a very common polymer in battery cells, and it really needs to be eliminated from those cells because it leads to self-discharge. Polypropylene is a much better choice. We recommend, that cell manufacturers use that tape. It's almost the same cost, only has advantages. And sodium-ion cells that are charging to 3.8 volts can have a better cycle life than LFP graphite cells. So with this, I want to thank Tesla for the funding, and thanks very much for listening.